Welcome everybody to Algebra 2, Section 6.6, Solving Radical Equations. So before we start actually talking about radical equations, I first want to recap how you solve a squared equation or quadratic equation by square rooting specifically. So if I were to have, let's say, 3x squared plus 4 equals, I don't know, let's go with the number 13. I would need to get whatever is being squared by itself first. So my first step would be to subtract the 4, giving me 3x squared equals 9, and then divide by 3 on both sides, giving me x squared equals 3. Now I need to undo the square by doing the opposite of squaring. Now we learned the opposite of squaring is to square root something. So we'll square root something on both sides. This gives us x, and on the other side we learned that when you take a square root of both sides, you get the positive and negative number. And so you get positive and negative 3. Now that's actually true when we do any even root, so it's true for fourth root or sixth root or eighth root, but we only learned for square root originally. And this was the basics of how we learned how to square root things, was we had to undo the square by square rooting. And what we're doing today is the opposite of this. We're going to undo square roots by squaring. Just kind of how we undo addition by subtraction, and the opposite way, we undo subtraction by addition. So we'll have a lot of the same steps here. So step 1 here is to isolate the radical or the root on one side of the equation, and sometimes we'll see it written as an exponent or a power instead, because you may remember that we can rewrite roots as powers. And then we're going to raise each side of the equation to the power of the index, and this will thus undo or eliminate the radical sign. And then we're going to solve the remaining equation. And then step 4, we have to check for extraneous solutions. It says to check for extraneous solutions all the time, but I will say that you don't have to check all the time. I'll talk about more in depth when you need to check. So number 1 here, we need to get whatever's inside the radical. We need to get the radical isolated. Let me clarify that. The radical needs to be isolated. So we need to get rid of this plus 5 because it is not part of the radical. So I'm going to subtract 5 on both sides, giving me the square root of x equals 7. Now that I have my radical by itself, I can undo the square root. So just like I undid the square by square rooting, I undo the square root by squaring. And those undo each other, giving me whatever's inside the radical, aka the radicand, which is x. And whatever I do to one side, I have to do to the other. And so I just square 7 and I get 49. And that would be my answer. X equals 49. It's by itself. It's done. Now you're more than welcome to check your work on any of these problems, even though I said you don't have to check them on every single one. You only have to check them in certain scenarios that we'll talk about. So how you check it is plug it back in, just like always, and the square root of 49 is 7, and 7 plus 5 does equal 12. It does, in fact, check out. And our concern as far as when we're going to have to check it would be if any even root were to equal a negative number. If an even root ends up equaling a negative number. So if at this step you were to have the square root of x equal a negative number, you would end up with an extraneous solutions, because an even root, such as a square root, cannot equal a negative number. It's without having it be imaginary, so it's non-real, and thus we're calling it extraneous because we're only doing the real solutions today. Number 3 here, we're going to try to get our radical isolated. So this time, I either can subtract 3 and then I'll have to get rid of this negative by dividing both sides by -1 or multiplying both sides by -1, or I can just add the fourth root of m to both sides. So I'm just going to do that, giving me 3 equals the fourth root of m. Now I have to undo the fourth root of m. Well, similar to how I undid the square root by squaring, I undo the fourth root by raising it to the fourth power. We just match the root and the power together. So for example, if I had the sixth root, I would do the sixth power. The eighth root, the eighth power. The 7th root, the 7th power, you name it. And because I raised one side to the power of 4, I have to raise the other side to the power of 4. Well, 3 to the power of 4 is 81, and on the other side, the 4th root and the power of 4 undo each other, giving us just m. So m equals 81. And the even root did not equal a negative, so we don't have to be concerned about any extraneous solutions here. On to number 3, this time a plus 7 is all underneath our radical, so we have to isolate all of that, meaning we just have to subtract by 10 before undoing our radical. So I will get the square root of a plus 7 equals 1 after I subtract by 10 on both sides. Now to undo the square root, I square. Remember, if you don't see an index here, you assume it's a 2. And a square on the other side as well, giving me a plus 7 on the left, whatever's inside the radical, even if it's multiple terms, and 1 on the right. Now, I'm not done yet because my variable's not by itself, so I have to get a by itself by subtracting 7, giving me a equals negative 6. So we got a negative number, so do we have to check here? Are we going to have an extraneous solution? The answer is no to both, actually. And the reason why is, once again, our radical, or even radical, is not equaling to a negative number. It equals a positive one. So if you were to plug back in negative 6 to check, you would notice that it works out just fine. You get negative 6 plus 7 underneath the radical, which is 10 plus the square root of 1. And last I checked, the square root of 1 is just 1. And so 10 plus 1 is 11, and it works out just fine. So it's okay that our answer was negative, but what we're not okay with is if our even root were to equal a negative number. Moving on to example 4. We have the square root of 6w minus 5 plus 10 equals 3. So we have to undo this addition of 10 in order to get the radical by itself by subtracting 10. So we get square root of 6w minus 5 equals negative 7. And so here you should have alarm bells going off that we have the root equal to a negative. So we'll go ahead and square both sides. And that gives us 6w minus 5 equals 49. Because when you do a negative times a negative, you get a positive. We add the 5 to both sides to try and get w by itself, and we get 6w equals 54. Then we divide both sides by 6, and I get w equals 9. But if I were to plug back in my answer to the original problem, square root of 6 times 9 minus 5 plus 10 equals 3. We get square root of 54 minus 5 plus 10 equals 3, which ends up being square root of 49 plus 10 equals 3, giving us 7 plus 10 equals 3, and that's just not true. 7 plus 10 most certainly does not equal 3, it equals 17. So this means that this is extraneous, and because our only solution is extraneous, doesn't actually work when you plug it back in to our root, our square root, and we restrict square roots to only being positive numbers. We restrict the radical function only being positive numbers for even roots. We say that this has no solution. Now you may be wondering, hey, once I'm at this step right here, and I clock that, hey, I have my even root equal to a negative, do I have to go further? And quite honestly, my answer to you is no, you don't. If you just want to jump straight to no solution, be my guest. That's what I do. But if you feel so inclined to go further, then please go further. And if you don't notice that, then go further, and then please check your work. And so the alternative to thinking critically about this and saying, hey, when do I need to check it, and making sure you're always aware of that and looking out for that, is to just always check your answer. Moving on to number 5. So So here, we don't see a radical, but we see an exponent of 1/2. Well, you may remember that when you see something with an exponent of 1/2, in this case c minus 12, that it's the same exact thing as c minus 12 having a root of 2, the denominator, with an exponent of 1, the numerator. And so it's the same thing as the square root of c minus 12. And so you're welcome to rewrite it as a square root if you want to, or you can just leave it as an exponent. I'm just going to leave it as an exponent. I'll show you how it works. I apologize. My oven is finishing preheating here, so that is the beep you're hearing there. It's quite a happy sound. It really wants us to know that it's at temperature. But anyway, what you do on this problem is you would still try and get this isolated, treating it just the same way as we are treating our root or radical. And so we're still going to divide by -9 because -9 is multiplying with our root radical, or what's being raised to a power in this case, which is the same thing as a root or radical. So I get positive 4 equals c minus 12 all being raised to the power of 1/2, or which is really, once again, the square root of it. So now I need to undo the power of 1/2. Well, how I undo the power of 1/2 is I want to try and get this to be just a power of 1. If I get that just to be a power of 1, that's just c minus 12. So I need to think, okay, what can I do to accomplish that? Well, if I raise this to the power of anything, the new exponent is going to multiply with this exponent. So what could I multiply 1/2 by to accomplish it going back to 1? Well, any number times its reciprocal will accomplish that. So we're going to have it raised to the reciprocal, or more importantly, really, the denominator over 1. And so we're going to raise it to the power of 2 over 1. Or just 2. And those 2's on the right reduce, just like we mentioned they would, and we just get c minus 12. And we get 16. And now we just keep solving like we would have before. So we still squared it, which is the exact same thing you would have done over here if you had a square root. So it still turns out the exact same, whether it's a square root or whether it's a power of 1/2, just so you're aware. So now if I add 12 to both sides, I get c equals 28, which I don't have to worry about extraneous solutions, since my even root, denominator of 2 is an even number, is equal to a positive, not a negative. Moving on to example 6 here. This is what's being raised to a power. This time I'm being raised to the cube root, or the 1/3 power. So I will subtract 11 from both sides, giving me the quantity of 7p minus 1 to the power of 1/3 equals -4. Now we notice, hey, we have this power radical equal to a negative. Is that going to be a concern for us? The answer is no, because this time it's not an even root, it's an odd root, and it's perfectly fine for odd roots to be equal to negatives, because we can take the odd root of negative numbers just fine. So we raise each side to the power of 3, and these 3's reduce, or well, 3 over 1 if you'd rather, giving us 7p minus 1, and then -4 to the power of 3 is -64. So I add 1 to both sides, giving me 7p equals -63, and then I'm going to go ahead and divide both sides by 7, giving me p equals -9. And while I could definitely check my work if I wanted to, I don't need to, because once again, this was an odd power, or an odd root, excuse me, not an even root, so we don't have to worry about extraneous solutions. On number 7, we're back to an even root, and we're back to writing it with radicals, with a 4th root. So I'm going to add 9 to both sides to undo subtraction of 9, and that will isolate my radical. So the 4th root of 8k plus 12 is equal to -2. So I can clock right away that, hey, I have an even root equal to a negative. No solution, and I can move on. You could raise each side to the power of 4. I was about to say multiply, but it's not multiplying. It's raising to a power. It's a different operation than multiplication. You could raise each side to the power of 4 if you really want to and go through and solve it. If you do, I'll let you know that you would end up getting k equals 0.5, aka I could write it as 1/2, which would then obviously, like I mentioned, be extraneous because as you plug it back in, it would not work because you have an even root equal to a negative number. Number 8 here, we have to undo this -4 and this +18. So I recognize it equals a negative right away, but that's not a concern to me. What's going to be a concern to me is that if it equals a negative by the time we have the radical isolated. We actually had the same thing occur here on number 5 where it equaled a negative right away, but by the time we had the radical or the exponent isolated, it was positive. So I'm going to subtract 18 from both sides, giving me -4 times the square root of 43 minus 3x equals -20. So if I divide both sides by -4 now to undo the multiplication of -4, I get square root of 43 minus 3x equals +5. So now it's a positive, so I'm no longer concerned about this whole negative deal going on. And so I can just raise each side to the power of 2, or square each side, giving me 43 minus 3x as it undoes the radical, or square root. And on the right side, I get 25. If I subtract 43 on both sides, I get -3x equals -18. Dividing by -3 on both sides, I get x equals 6. And that would be my answer. Moving on, we'll look at number 9. Whoa, we have 2 radicals. We should panic. No, you should definitely not panic. Instead, we have to think, okay, well, what do we do? Well, good thing I'm here to help you. So we look and say each radical is actually isolated. They're both by themselves. And so in a scenario where you have multiple radicals, you actually just make sure they're separate. They're on separate sides of the equal sign. And then you undo them. And we'll only do problems where they're the same index or root. It is technically possible for them, it is possible for them to be different ones. Like this could be a square root, while this could be a third root. And then you'd have to raise them to a common power that would undo both, such as in this case, like the 6th power. A way to think about that would be if you were to convert these to exponents, is a good way to think about that. To say, hey, this is the power of 43 minus 2u, the power of 1/3. What exponent can I raise both of these to undo the 2 and the 3, to reduce the 2 and the 3 as we cross reduce those? And 6 would fit the bill. It ends up just being the least common multiple, the lowest number they multiply up to undo that. And so it can work out just fine. But anyway, regardless, here in this class, we'll only do when they are the same radical, or same index or root. So we're going to square both sides, and on the left, square the square root, you undo it, and you just get u minus 8. On the right side, the same thing happens, and we just get 43 minus 2u. And this is just a run-of-the-mill equation now, to where I have to get my u's on one side, my numbers on the other. So I'm going to go ahead and move my smaller u by adding 2u to both sides and getting 3u. And in the same step, I'm going to go ahead and add 8 to both sides to get that away from my variable, giving me 51. So now if I divide by 3 on both sides, I'll get u equals 17. Now, here's the thing. When you have a radical on both sides, you do actually need to check, because there's no way to be able to know if your even radical or even root were to have equaled a negative or not before we squared both sides or undid the radical. So we have to plug it in to make sure that neither one would equal a negative. And so our concern is purely that either radical would end up negative. So if you're able to tell, for example, like this one, that, hey, 17 minus 8 is positive, or at least at the very least it's non-negative, it's 0 or positive, then you don't necessarily even have to plug it in formally, writing it down to the left-hand side. And same thing here. If you're able to say in your head, hey, 43 minus 2 times 17, oh, okay, I know what number that's going to end up being. And that's, or at the very least, you can say, oh, that's for sure not a negative. Then you can just move on and call 17 your answer and not have to worry about checking. Because you did all the checking you need to. Because once again, our only concern is that we're going to have an even root that is either has a negative inside of it or is equal to a negative. Those are our concerns. But as we go and just plug these in, for those of us who are going to be more visual with this, 17 minus 8, and the square root of 43 minus 2 times 17. So that'd be the square root of 9 equals the square root of, my 9 didn't write very well, 43 minus 34. And so this ends up being 3 times the square root of 9, which just is factually accurate. And so u does equal 17. And once again, our only real concern was that neither radical had a negative radicand or a negative number underneath, since they were both even radicals. Moving on to number 10. Once again, we have 2 radicals on each side, or a radical on each side is to be 2 radicals total. And so I'm going to have to undo the 4th root. They are on separate sides, though, thankfully. If they weren't on separate sides, we'd have to add or subtract one of them to move it over to the other. And so I'm going to go ahead and take each one to the power of 4 to undo the 4th root. So I just get whatever's inside. 27 minus 2d and 2d minus 3. So as I move my smaller d to the other side, I'm going to add 2d, giving me 3d on the right side. And as I move my number away from my variables, I'm going to add 3 to both sides, giving me 30 equals that 3d. And so now as I divide both sides by 3, I get d to equal 10. And once again, we need to verify that the inside of the radical will not be negative, since they're both even radicals. If they were odd radicals, such as or odd roots such as 3, 5, 7, we would not care. We just call it good. Okay. But once again, we do care. We want to make sure they're not going to be negative. And so if we plug it in here, we can say 27 minus 2d. That ends up being 27 minus. Why did I write 2d? I should just write 2 times 10. Silly me. That ends up being 27 minus 20. And I can already tell it's not going to be negative. 27 minus 20 is a positive number because the bigger number is positive. It's square root of 7, by the way. And so I can just move on. And then I should note that this is technically the 4th root. And then I can do the other side and say the 4th root of 10 minus 3. And once again, I can note, hey, that's actually already just positive. It's not going to be negative. And at that point, as soon as I know that I will not have an even root of a negative number, I can call my answer good. You don't necessarily have to go through the whole equal thing. You don't have to wait until you get all the way down to, hey, the 4th root of 7 is equal to the 4th root of 7. Yes, I've confirmed that both sides get the exact same thing. Really not necessary to do, but always an option to do if you want to just check your work. Now, number 11 here, we have some stuff outside radicals. So we have 2 radicals on each side and things outside. So you could just square immediately here, and sometimes we have to. But you could also choose to get one side clean. And how you would do that is undo the multiplication. So we could choose to either divide both sides by 12, which would give you a fraction, and that's not very fun. Or you could divide both sides by 4, which would not give you a fraction here, nor here, and only make your numbers smaller. I'll talk about what you would do if you didn't divide. It's not that much different at the end of the day. You just get some bigger numbers. So this gives me the square root of 3q plus 15 equals 3 times the square root of q. And so now we've done as much simplifying as we can. So now we're going to go ahead and undo the square root by squaring both sides. And you square the entire side, so including that 3 outside the radical. On the left-hand side, the square root undoes the square, and you just get 3q plus 15. Let me make my q a little more clear there. On the right-hand side, it might be helpful for some of us to actually see this written out, that it's 3 times the square root of q times 3 times the square root of q. That we end up getting 3 times 3 is 9. Square root of q times square root of q is just q. And so we end up getting just 9q from this. And essentially what happens is you square the 3 and you square the square root. Because there's a secret exponent of 1, you do the 1 times 2, which gets you 3 squared. And remember, you can only multiply this exponent inside when there's no addition or subtraction inside. If it was like 3 plus the square root of q, you cannot do that. You'd have to write it twice and multiply them through. But now let's go ahead and finish this problem here. We'll subtract 3q from both sides to get the q's all together and away from the numbers. So I'll get 15 equals 6q. And then if I divide both sides by 6, I end up getting a fraction or a decimal. I like to write my answers as fractions personally. So this reduces by 3 and giving me 5 over 2. And notice I shifted my q to the left-hand side. I just do that out of habit. The q is more than welcome to be on the right-hand side. And I should actually note, I do need to go back and check to make sure that I won't get any negatives. But real quick, as I check to make sure I won't get any negatives, if I plug a positive number in, I won't get a square root of a negative. And the same thing's true here. If I plug a positive number into this, 3 times another positive number, if I add whatever that result is to 15, it'll only get bigger and more positive. The only way that I could have something on this problem specifically produce a negative inside the radical is if the q itself was negative, and then that would make this one negative. And if it was a big enough negative, then it would make this one negative too, as it multiplies with 3 and adds with 15. Number 12. So here we have cube roots, 1 on each side. We have a negative 2 out in front. Oh, sorry, let me go back to 11. I did mention I was going to say, hey, what would you do if, in this what if scenario, for us not multiplying or reducing by 4. So let me talk about what you would do if that were to be the case. So you would square both sides. Right away, actually. And what ends up happening is you square the 4 and the 3 square root of 3k plus 15, and you just get 16 times 3q plus 15. I have to put that in parentheses because it's going to be distributing in a moment. And I get 144q as I do 12 squared and square root of q squared. And so on the left, I end up distributing, giving me 48q plus 16 times 15. Let me do some math here. 240 equals 144q. And so I subtract 48q from each side, giving me 240 equals 96q. And if I divide each side by 96, you'll never guess what happens. That's a little bit of sarcasm. You may guess what happens. Some of us may not right away, but you may guess. It reduces to 5 over 2, which is the same exact answer. So you get the same exact answer, just with a little more work. And sometimes this is our only option, actually, because you... actually, I guess it won't be our only option, I should say, because you could always divide, undo one or the other. But sometimes it might just still be our best option to avoid fractions, perhaps. But regardless, that's how you would do that problem. And some of us may benefit from seeing this written out as well. So to be clear, what that would be is 4 times the square root of 3q plus 15 times 4 times the square root of 3q plus 15. And 4 times 4 is 16. And then 3q plus 15, the square root of it, times itself, would be 3q plus 15. But you have to remember that you can't just multiply 16 times 3q or 15. You have to do the whole thing, which is how you got the 48q plus 240. But anyway, that's not how we chose to solve it. We chose to solve the other way. Moving on. So now on number 12 here, cube roots, one on each side. We have a -2 outside of one radical and nothing outside the other. So there's no way to get rid of this -2 because if I divide both sides by -2, I'm just moving the problem and creating a fraction. So I'm not making my life any better at all. So I might as well undo the power or the cube root by doing a power of 3 or raising to the power of 3. So on the left-hand side, I undo the cube root by getting 14 and giving us 14 minus 10n. On the right-hand side, as I cube each, cubing -2 gives me -8. Be careful with the negatives, though, because if it's an even number of negatives, an even power, that'll produce a positive. And then on the cube root of n being cubed is n. And because there's only one term underneath the radical, I don't have to distribute the -8 to anything. And now I will move my smaller n by adding 10n to both sides and move it away from my variable, away from my other numbers, rather. And so I get 14 equals 2n, and I'll divide by 2. Oh, my n didn't write. Now I'll divide by 2, giving me n equals 7. Moving on to number 13, we have a radical on one side, not on the other. So this is the ideal time to square on both sides. And so I square on both sides, and I get 8x on one side because it undoes the radical, and on the other side I get x squared. So we have x being squared. So this means that we need to start solving how we solve quadratics. And we can't square root again because that just gets us back to the same problem we were just at, right up here. It undoes what we just did. So meaning we need to set it equal to 0 and look to factor in order to solve. So I'm going to subtract 8x from both sides, and I'm just going to flip it around at the same time, giving me giving me x squared minus 8x equals 0. Once again, I subtracted 8x from both sides, and I flipped around my equation. So technically an in-between step would have been 0 equals x squared minus 8x. Moving on from that, I'm going to go ahead and look for a GCF first. There is a GCF, and so I factor out a GCF of x, and I get x minus 8 equals 0. And I have two terms inside the parentheses. Whenever I have two terms, I want to look for either a difference of squares, difference of cubes, or sum of cubes. Well, it can't be a sum of cubes because it's not adding, and it can't be a difference of cubes because even though 8's a perfect cube, x is not a perfect cube. If it was x to the third, it would be. And it can't be a difference of squares because neither of these are perfect squares, meaning it's actually just already all factored out. And if you're wondering, this wasn't either a difference of squares or difference of cubes either, because once again, neither of those are perfect squares or cubes. So now we'll set each of these equal to 0. So x equals 0. That one's already solved. Good for us. Oh, I should actually clarify what I want to check that. And then x minus 8 equals 0. And so I'll add 8 to both sides, giving me x equals 8. So like I said, we'll want to check these to make sure that since we have multiple variables here, it brings in another element of when we want to check. And we want to check that neither variable will, quote, screw this up. We'll make it so an even root equals a negative, or you have an even root of a negative. And so if I plug in 0, it doesn't make this negative, and it doesn't make this negative, so we're fine with x equals 0. And if I plug in 8, it doesn't make this negative, nor this negative, and so we're fine. So it doesn't make the radicand or inside the radical a negative, and it doesn't make what's outside the radical or on the radical is equal to negative, which would be the two concerns. Let's look at number 14 here. Number 14, back with only one radical again, but multiple variables. So radical's right here. Undo that by moving the 7a. So we subtract 7a. Square root of 12 minus a equals 1a or a. Now we'll square both sides again, just like we did on the last problem, and giving us 12 minus a equals a squared. Again, now we need to solve this, and spoiler alert, whenever you have a variable being squared on these problems, you're going to have to set it equal to 0 and factor. So I'm going to add a and subtract 12, as well as flip it around. So add a, subtract 12. And of course, whatever you do to one side, you have to do the other. And I'll flip it around as well, like I mentioned. A squared plus a minus 12 equals 0. You might be wondering, Mr. Crossell, why didn't you just subtract a squared instead? And the reason is we always want our leading term, our a squared, to be positive, not negative. It causes some issues with the x when we factor, if it makes it negative, if it leads a negative, excuse me. And so then we'd want to factor out a -1 from everything, causing an additional step. So I have 3 terms, and I look for a GCF. There is none. And so I go ahead and make the x. And as I make the x, I do a times c at the top, which is 1 times -12, which is -12. And I do b on the bottom, which is a 1, because it's a 1a. And I look for 2 numbers that multiply at the top and add to the bottom. Well, one would be a negative and one would be a positive in order to multiply to a negative number. And it would be -3 and +4 in order to add up to +1 while multiplying to -12. Thankfully, I can, in fact, use a shortcut since it's a 1a squared. And so I make my 2 factors, and I get a minus 3 and a plus 4, taking our variable with half the exponent, for the new exponent of 1, and the number and sign from the sides of my x or puzzle there. And this equals 0. And so now we have to solve each of these equations. And so I have a minus 3 equals 0, and a plus 4 equals 0, giving me a equals 3, and a equals -4. Once again, our concern is that we would get an even root of a negative inside of it, or an even root equaling a negative. So we're really looking at this step in the problem when a radical is by itself. If I plug in +3, that gives me the square root of 12. I'll erase that arrow real quick. That gives me the square root of 12 minus 3. That's 9. That's fine. And if I plug in 3 here, that's fine too. So, and yes, they do equal, the square root of 9 is 3. If I plug in -4, though, I notice that this is fine. It ends up getting me 16. But this causes an issue. I would have that 16 equal to -4, and the square root of 16 just is not -4. Meaning that this individual answer is extraneous, because it would cause it to equal a negative. I will actually show that being worked out as well, that some of us may benefit from. So the square root of 12 minus a -4 equals a -4. And so that would end up being the square root of 16 equals -4. And the square root of 16 is 4, which, once again, anytime you have an even radical equaling a negative, that's an issue. So our only answer is 3. But we did have to find -4 as part of the problem and then label it as extraneous. It's all part of our answer. Moving on to number 15. On number 15 here, we have a radical by itself, so we're going to go and look to undo that by squaring, and we square the whole side here. Now it's going to have some implications on the right-hand side that we'll have to talk about in a moment. To the left, though, we do 6m minus 38 as it undoes itself. Now we can't just do this here because there's a minus or a plus sign in it. And so instead, we have to write it out twice. And I'm just going to do this off to the side to keep my main problem a lot cleaner. And so I'll just do it over here and have m minus 5 and m minus 5. And as I do that, I get m times m is m squared, m times -5 is -5m, -5 times m is -5m, and -5 times -5 is +25. So combining like terms gives me m squared minus 10m plus 25. And so now I'm going to write that in the blue. M squared minus 10m plus 25. And since I have an exponent of 2 on a variable, I will need to set this equal to 0 and solve. So I'm going to subtract 6m from both sides. and add 38 to both sides and combine those with the like terms. I'm going to go ahead and flip it around so it equals 0, 2 on the right, because that's just how I prefer my problems. So m squared minus 16m plus 63. So now we're going to go ahead and look to factor this. So it's 3 terms. We look for a GCF. There is none. We go ahead and make the x. And it'd be 63 on the top, negative 16 on the bottom. And the sides of this x would end up being negative 7 and negative 9 in either order. We can use the shortcut since it's a 1m squared. So we do m minus 7 as one factor and m minus 9 as our other, equal to 0. Set each of these factors equal to 0 individually. And then solve, so you get 7 and 9. But since there's a variable outside the radical, we do need to verify that we will not be causing there to, by plugging m in as 7 and then as 9 as well, we won't be causing it to be a negative underneath the radical or the radical equaling a negative number. So for example, if I plug in 7, 7 times 6, we have to ask, is it 38 or bigger since we're subtracting 38? The answer is that it's 42, which is bigger than 38, so not creating a negative, so we're fine there. And then 7 minus 5, once again, not creating a negative, so we're fine there. So m equals 7 is no issue. 9 times 6 is bigger than 42, so it's not an issue. 54 minus 38 would be perfectly fine. And then once again, 9 minus 5 would also not be an issue. So these are both perfectly fine answers. Moving on to number 16 here, we have our radical or our square root already being isolated, and so we're just going to go ahead and square both sides. So left side, we just undo the square root and just get 2v plus 3. On the right hand side, we are going to have to multiply or FOIL this again. And so I'm going to do v plus 2 times itself, giving me v squared, 2v, 2v, and 4. And combining this, I get v squared plus 4v plus 4. So I'll write that back in my equation. And so now I'm going to go ahead and set it equal to 0 by subtracting 2v and subtracting 3 from each side. And that'll give me a 0 on one side, but I'm just going to flip where that 0 is. I get v squared plus 2v plus 1. And so now 3 terms, I look for a GCF, there is none. So I'll go ahead and make my x. And as I make my x, I end up having 1 at the top, 2 at the bottom. And 1 times 1 multiplies to 1 while adding up to 2. I can in fact use my shortcut, and so I get v plus 1 and v plus 1. And so now I set each of these equal to 0. And I end up getting both of them to be -1. Just the same answer twice. And so when I plug 1 in, I really get to just plug them both in at the same time, which is nice, convenient here. Let me emphasize the negative on this first, or the answer is a little bit better. If I plug in a -1, I don't want it having negative in either radical, and so I get -2 plus 3, which is non-negative. In fact, it's +1, so no issues. Plug it into the right-hand side, I get a non-negative. In fact, I get the answer of 1, because -1 plus 2. And so these are perfectly fine answers. Moving on to number 17 here. Once again, have a radical isolated. So now we will once again square both sides, undo the square root. And so on the left-hand side, we'll get 51 minus 5y. On the right-hand side, we'll again have to write this off to the side. Giving me y times y is, let me emphasize this, was a parenthesis, y squared, negative 11y, negative 11y, and positive 121. Combining to get y squared minus 22y plus 121. So I'm going to subtract 51. It's protesting me writing this down, I suppose. Caught up, but kind of. Oh, I have to rewrite my 121. There we go. And add 5y on both sides. And I'll flip around where my 0 is again, just for personal preference. And I get y squared minus 17y plus 70. I look for a GCF, there is none, so I go ahead and make my x. As I make my x, the top is 70, the bottom is negative 17. Two negatives would do the trick, and specifically negative 10 and negative 7. I can use the shortcut since it's a 1y squared, so I get y minus 10 as one factor and y minus 7 as the other. So I set each of these equal to 0. And as I solve, I end up getting y to be 10 and y to equal 7. And once again, since I have an even radical, I need to make sure that the radicand, or what's inside, would not become negative as I plug it back in, and that the right-hand side would not equal a negative, so an even root would not equal a negative. So I'll practice plugging in 10. And I get 51 minus 50, which is perfectly fine. So now I plug it into the other one, and I get 10 minus 11, which is negative 1. So that one's extraneous. So that's good to note. So I'll mark it as such. Extraneous. And now I'll try y equals 7. So I plug y equals 7 here. And I get 51 minus 35, which is 16, so that's perfectly fine. But as I plug it in here, I get the same exact issue. I have 7 minus 11, which is negative 4. So this one is also extraneous. And since they're both extraneous, I can actually just state that there is no solution after all. On to number 18. Number 18 is a very unique problem, to where we have subtraction outside the radical. So we still have a radical separated the best we can, so we're going to go ahead and square, because the only thing you could do, I should say, is add 1 to both sides, which just moves where the 1 is. And it doesn't really help you. So you're more than welcome to do that, but it's quite unnecessary. If you want to, it's fine. I just personally would rather just not do the step. And so I'm just going to go ahead and square both sides. So on the left, I just get x plus 9. On the right, I can't just call it x minus 1 or plus 1, but instead I do have to actually write it out twice, since I do have a minus or a plus sign in between. And so I get square root of x minus 1 and square root of x minus 1. And I do go ahead and FOIL this through. Square root of x times square root of x is just x. Square root of x times negative 1 is negative square root x. Negative 1 times square root of x is the same, negative square root x. And negative 1 times negative 1 is positive 1. And so I get x minus 2 squared x plus 1 as I combine these common radicals. And so I'll plug this back in on the right hand side. Oh, I wrote 2 into 2 squared x. And now we have to solve this a little bit differently. Since we have a square root rather than a square, we're not going to get it set equal to 0. Instead, we're going to do what we do every time we have an equation with a radical, is we isolate the radical. And so I have to subtract x from both sides and add 1, so we subtract 1 to both sides. If I wrote x. So that'll give me no x's on the left. I just get 8 equals negative 2 squared x. And now I have to divide by negative 2 to still continue getting my square root of x by itself. And so I get negative 4 equals the square root of x. Now you may already notice at this point that we have an even radical, an even root equal to a negative. And so if you notice at this point, then good for you. But if not, we can continue solving and squaring this. I wrote a 2 instead of a parenthesis. And that gets you 16 equals x as your answer. But it's a non-answer because if you were to plug it back in, it would not actually work. For example, even right here, you'd have the square root of 16 equals negative 4, which is not a true statement if you plug it back into the green. And if you plug it back into the original problem, it wouldn't work either. You end up getting the square root of, I'll use a different color to make it pop a little bit better. I'll do it over here. The square root of 16 plus 9 equals the square root of 16 minus 1. And the square root of 16 plus 9 is the square root of 25. And that would equal 4 minus 1, allegedly. And so this would give us 5 equaling to 3, which just is inaccurate. And so we say, okay, well, that's not true. And because that's extraneous and not true, there is no solution. And I mentioned that some of us may have noticed earlier at this step in the green that we have a square root or an even root, more specifically, or more generically, I should say, equal to a negative, thus creating a no solution scenario. Before we even bother doing the purple, you can notice that and just jump to no solution. And that wraps up section 6.5 of Algebra 2.